Hi everyone, my name is Doug. Some of you may know me because I wrote a book, Relevant Search, a couple years back. I think it's still relevant, and that's my only dad joke for the day. I originally did a version of this talk with Tommaso Teofili, a colleague of mine who works at Adobe. Tommaso is writing in progress deep learning for search. And Manning was nice enough to give us this discount code, and I think it's 40% off, but don't hold me to that. Sorry, it's at the bottom. Yeah, I was in the back in this room earlier. It was a little rough. There's a dog running around back there. That's what I mean. Okay, so we're going to talk about relevance today, and we're going to talk about aboutness. And the theme of this talk is really aboutness, and I got a lot of stuff to get through. And really what I want we talk about when we issue this query, Bitcoin regulation, how are we going to rank the documents that come back? And for the longest time, we've had this sort of this notion of aboutness. We think that document 2, we try to get at some measure. The document 2 is closer to the query's intent than document 1. It's more about the query than document 1. So we rank it higher, right? And of course, one hypothesis, and of course I think finally we're at the point where we treat this as a hypothesis and not like the way just the search engine works and we move on, is that TF-IDF is a measure of aboutness. If we figure out the document that has more proportion of Bitcoin in regulation, more proportion of the corpus is Bitcoin regulation terms, it's probably closer to the query and more about the query. And that's one hypothesis. Sadly, that doesn't always work. And those in the back can't see the Homer Simpson hitting his head on the ceiling here. But if you watch anything, there's so many demos like build a solar app in 5 minutes or whatever, ingest a bunch of documents, you're searching right away. And it's interesting too because there's a whole other step down here. If you go to like DrupalCon and you try to talk to them about relevance, they're like, what are you talking about? I put all my data in Solar and it just is way better than the SQL-like statements that Drupal does. So like this, trying to get here with those Drupal folks, it's like there's probably something past here we haven't thought of yet, right? So you can spend a lot of time on your relevance and features work trying to move up the quality spectrum. And of course, it all assumes we know how to measure quality, and that's always an assumption that gets violated constantly. The best search companies I know obsess about that, and they don't take it for granted. And why is this so hard? I mean, there's a bazillion reasons. There's searcher vocabulary mismatches with the content. The searchers expect context, personal, emotional. Like, I searched for, that I'm a Solar expert. Why are you giving me the Elasticsearch filter factory? That sort of stuff. There's all kinds of different entities to match on in the query. Language changes and evolves. The first versions of Google probably weren't dealing with WTF and those sorts of things. Just misspellings and typo. There's all kinds of different things in our documents we want to match on, sometimes title, sometimes people. And finally, depending on what our intent, TF-IDF just doesn't matter. Sometimes it just doesn't match or not. So a lot of different things there. So this is actually not the title of the talk. It's probably, I'm going to rename this talk to There's Something About Aboutness, or maybe The Hunt for the Red, or About October, or this one I didn't have to change the title at all, The Last Sharknado, It's About Time. So that's the talk you're about to see. So how many people have played around with embeddings of some sort? Like word-to-vec, LDA, latent semantic analysis. All those things have been out there actually for a long time. What an embedding does, we're going to ask the question, is embedding a way of measuring aboutness? And this is something that people, I feel like this is, TF-IDF was an assumption from 10 years ago or so. This is an assumption from a couple years ago that I think is a bubble that may have finally burst. A vector, what a embedding is, of course, is a vector that's storing some context. And I apologize to the people in the back. But I got hacking on my Bitcoin server. It's not hyped. Have you heard the hype about Bitcoin currency? Bitcoin, a currency for hackers. Have you heard the hype about Bitcoin currency? I guess I copy-pasted that one. But you can see a lot of the same kinds of words tend to gravitate around this Bitcoin statement, right? So we have a lot of context, and we can encode that context into a vector. And of course, it's much more than 2 dimensions for the most part, but it's way easier to show it on the graph if we have 2 dimensions. So these 2 terms occur in similar contexts, Bitcoin cryptocurrency, right? You know, if we get them on a graph, we can see that pretty easily. And we can do the same operation. We can treat the full document or parts of a document as context and encode a similar vector for the document itself. And we can build a search system that's more or less based on this idea. Bitcoin cryptocurrency, doc1234, that thing we just saw last time that I'm sure everyone read in the split second the thing was up, is higher than this other document. And okay, this seems like a good approach for aboutness. Is this a good idea? And I'm going to trip and fall, and I think I wrote my emergency contact information in my phone just for everybody. Unfortunately, this is an invalid assumption. Sadly, there are many things that share similar context but actually have opposite meanings. And this is a key lesson when you're getting started with something like Word2Vec and Doc2Vec and all those. Cancel and confirm, this is a very classic chatbots use case that you see a lot. I want to cancel my reservation. I want to confirm my reservation. The exact same context, talking about reservations, but very much the opposite meaning. So this is not the silver bullet we want it to be. And fundamentally, there's still a mismatch. You know, we have our Bitcoin hackers putting into our Bitcoin search engine about fiat currencies or have a global conspiracy against Dogecoin. And then, you know, someone like my dad is over here like, $BitDollar? Like, what's that? So this is search in a nutshell. Is we have these vocabularies that we are trying to map between what the search user is doing and what's in our index. So the first step when we talk about the neural frontier, and really when I talk about the neural frontier, I'm really thinking not in terms of that research paper that came out 6 months ago, or the hypothetical research paper that came out 6 months ago at Google or something. I'm thinking about things that are going to become everyday things that we do as relevance engineers in the kind of work we do. And I came up with this phrase yesterday called embedding modeling that I think is actually pretty important to our field and our practice. And it's going to be pretty important to how we actually do feature engineering. And you know, technically Word2Vec isn't really deep learning per se, but I think it's in the vein of that sort of technology. So, and the other thing I want to talk to you about is a lot of this stuff, you have to have an intuition for how something like Word2Vec works. And once you have an intuition for how this stuff works, you can build the $6 million man. You can build any kind of embedding you want to do anything you need it to do. And it's very similar to the idea right now where we have an intuition about how an inverted index works. We have an intuition about how Solr works, how we can do different things, how we can construct different queries. And I think there's an intuition under embeddings too to have. And the good news is it's not all AI machine robots that make us all obsolete. There's a lot of data modeling, data cleaning, and all that stuff that go into actually getting good embeddings. And now to terrify you, I've put up all this math. Anyone can understand how Word2Vec works. And I really recommend, if you're interested in the topic of deep learning, is to just take a pass and really just understand how Word2Vec works. And I'm showing one specific kind of Word2Vec, which is skipgrams and negative sampling. There's all kinds of stuff out there. But to get an intuition for how this works, really we just have, let's say this is a 300 dimension vector, an array of 300 numbers. We have 2 of them. We have Bitcoin, and for some reason I chose energy. Bitcoin and energy, let's say that they co-occur. So down here there's a table that says Bitcoin energy in same context 1. And then there's a prediction that the model's making right now that's 0.67. Now, this is a model that's just being fed forward with random numbers. And all that's happening are this random numbers, this random vector is getting multiplied together. This is just a dot product. The 0th element of each vector, the first element, the second, blah, 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 down to, 300th. And this is probably the most important thing in this whole model. And then there's this funny thing that you might have heard of called a sigmoid that squashes arbitrary numbers down to 0 to 1. And this is designed so that we can sort of try to work backwards and tweak these vectors so that that model prediction gets closer to 1 for things that share context, and is closer to 0 for things that don't share context. So everyone memorize this, right? It's going to be on the quiz. And my arrows always screw up, and I have to figure out the aspect ratio or something on these slides. But you know, how this works is we have this notion of negative sampling. So when you build an embedding, and this is one method, that I think it's a pretty interesting and intuitive method. You have two terms, Bitcoin energy. This is our training data. We know they share a context because we pulled it out of our corpus. And whatever random numbers we started with are starting out saying 0.67. And like I said before, we're trying to tweak this prediction up closer to the truth. And to help it out, we took some what's called negative samples. So maybe from the relative to the context these occur in, we just kind of go out to the index, randomly sample different terms that don't occur in this specific context, and say these aren't co-occurring. Let's try to push these down. And in that way, we're making that vector so that vectors of things that appear together actually kind of clump together on that graph we saw a while back, and things that don't just kind of get moved around. And where they actually show up is just completely random. It's just weights being tweaked. So, and this is really interesting because lots of negative examples is actually is a big theme in learning to rank as well. Like one of the big problems that people have with learning to rank systems is they don't have enough negative examples. And people can make tremendous gains by just having lots of negative examples. So this looks terrifying, you know, more math, right? But when you look at this is all this is our model that we just saw. We have 1 over 1 plus e to something is the sigmoid. That's just something that squashes things to 0 and 1. And honestly, there's a lot of different, this verging into deep learning, there are a lot of options for things you can use for squashing something to 0 to 1, right? Sigmoid is pretty popular. And this VC right there, that VC is the dot product. So V is our Bitcoin vector. C is whatever shared context we have. You know, here's our Bitcoin vector, and here's the negative context. And we're trying to maximize this guy. So this guy's going up. We want this fitness function to go up, right? We want this log that's going to hopefully turn to 1 is going to increase, and this one's going to, the sum of hopefully all these zeros we want to go down. So all we have to do is to remember our calculus that I'm sure we all love and adore, and do what's called backpropagation. And I hope what you're seeing here is all of these terms that come up again. The hook that you have to mastering deep learning and not being terrified by it is to really get into word2vec or doc2vec. I think I lost a slide. There's our backpropagation. So here's our fitness function, and it should be df. I called it a loss function before. And here's our Bitcoin vector. And we're saying, okay, we need to push this part of the vector to make it closer to the direction we need to go. We need either to get closer to, we need to push V0 up relative to the fitness function. So once we get that, and you can go and you can actually, I wouldn't necessarily derive this derivative. You can go and steal it from code, or you can go and look it up somewhere, and you can figure out how do I tweak V0 once I know which direction I need to propagate. So, and you just neural networked. It's not really a network, it's a neuron, but it's pretty much the basic building blocks of a lot of what's to come. So of course, and there's something, we can do the same exact exercise with documents. They call it a paragraph embedding. It need not be a full document. We have something that represents a paragraph. So here's our vector, again, randomly initialized, that's also going to be tweaked in the same fashion. And what do? We do the same exact exercise. We have Bitcoin, and here I've decided that paragraphs are parts of documents, but again, you can design this to do anything you want. These share a context. Bitcoin does occur in this paragraph of this document. Bitcoin does not occur in this paragraph of this document. So the word-to-vec model pushes these apart. So again, this is what this is a tool for us to learn context. And context can mean whatever we need it to mean for our domain and application. So really what we're doing is manipulating the constructions of embeddings. We want to manipulate something, the construction of embeddings to measure something specific to our domain and our field. So this is a clay that we can mold. We don't need to take what comes out of word-to-vec as gospel. And I was recently inspired by this blog article that came out of Airbnb, and I don't know if anyone here is from Airbnb right now. They were at Lucene Revolution in Austin. They gave a pretty good talk, but they talk about building listing embeddings around recommendations and personalization. You know, we're going to see, you know, all of this stuff that we're talking about, users can share context. And we're about to see some fun hacks. So there's a lot, you know, once you understand how this works, you can change your definition of context to mean and do lots of different things. So query and regulation, do they occur in the same session? And define session however you need to do what you need to? Okay, yes. Bitcoin and bananas, Bitcoin and headaches, Bitcoin and daycare, you know, they don't really occur in the same session. So we could sort of start to clump together query terms that tend to co-occur, or query phrases that tend to co-occur. One of the things I didn't talk about is that to use these well, a lot of the same, you know, a lot of the same things we do in Solr analysis chains, you have to do often before you get to word-to-vec. So figuring out phrases and that sort of thing. One question I ask is, if you have solid judgments, can we build embeddings from documents? If Bitcoin occurs in document 1, 2, 3, 4, and we know it's relevant, can we build a relevance-focused embedding that clumps together things that are relevant and pushes apart things that are irrelevant, regardless of what language occurs in here? I think this is really interesting. The challenge to this, and the reason that, you know, maybe you don't necessarily want to do this, is you need a lot of training data for this to work, which you tend to need anyway for learning to rank. But I suspect you might need more. Now another thought: you could pre-train with your corpus some embeddings. You know that Bitcoin is not going to map to $bit or whatever crazy thing your searchers are doing. But if you pre-train this, if you say, okay, we know these kind of co-occur, but maybe in this case, this is actually a truly relevant document, even though Bitcoin doesn't share any context in this document. So maybe this document is actually about the query term, even though nothing in a regular embedding would tell us that. So maybe we could sort of push that up and push this down. And I think the keynote speaker today talked about having strong priors, and the corpus word-to-vec can act kind of as a strong prior that can evolve over time of your, as you learn more about your query language. I like this idea too that Tommaso specifically came up with. Another thing you can do is just, if you have judgments, you can just say, okay, well, I'm going to sort of geometrically sort of just directly push the vector itself closer to the documents that it's relevant for. So maybe you don't do it just in one swoop. Maybe there's kind of a learning rate, so it's kind of wandering around because there's probably documents all over the place. But that's another interesting thing that I think is kind of fascinating. And of course, you could use embeddings to build, to create basically user embeddings or item embeddings for recommendation or personalized search. So Tom likes jeans, Tom doesn't like khakis, Tom doesn't like iPad, Tom doesn't like dress shoes. And you know, the same training process, we're pushing the embedding so that's predicting similarity and pushing another set of random numbers down so it's not predicting similarity. And Another thing we can do is introduce the idea, and you can see I like just have fun coming up with these ideas. Another thing we can do is introduce the idea of an embedding for a sentiment and sort of encode sentiment as a feature when we train embeddings. So cancel and confirm probably occur in opposite sentiments. So cancel is like, I hate you, cancel my reservation. Confirm is like, I love you, I want to confirm my reservation. So cancel co-occurs with in this document and as angry. So these all three are sort of in the same way that we might have a couple terms that co-occur in the same document. They very much occur, in the same context. We sort of actually build a vector for, we do actually build a vector for angry, and we build a vector for happy. So we see what groups with those. And we sort of start to do a bit of at least word sentiment analysis, probably not super accurate. But this can help sort of pull apart that confirm and cancel that go right on top of each other. Yeah?
Don't you have the opposite problem here? Let's say you have a corpus of newspaper articles. What's to prevent you from associating the word toxic with New York Times, failing with the word New York Times, or toxic with GMO, or other things that are common sentiments but not actually properties of the object?
Yeah, that's totally valid. That's a totally true concern. So like if you were looking at Twitter, you would probably pull out that there is an idea, you could probably group the sentiment actually with the term. So you have a vector that's a term sentiment and a term, like a term happy. So what are all the New York Times happies and what are the New York Times angries? And come up with two vectors for a term, one for each sentiment. That's just, I'm thinking of the stuff off the top of my head. That's just one thought I might have. It could be pretty cool. And finally, we sort of beat around the bush on this, is can you get to evolutionary and contextual embeddings, where as things evolve, you might start with a prior that's your corpus embedding model, but you're sort of pushing Bitcoin's embedding around all the time based on what happens with relevance. And this is a couple different ways. This is sort of like, okay, what's happening here? Oh, we noticed a signal or something in our analytics that meant this was a relevant result. So we just tweak it a little bit because it may have just been relevant for one crazy person, or we tweak this down a little bit. So there's all of these ways we can potentially build and train embeddings to do interesting things. And notice I haven't really gotten to anything that's deep learning. It's just cool embedding stuff. And I think focusing on the thing of least sophistication that gets the job done is a really powerful thing. And there's a ton more you could do here. Embeddings are fun to play with by looking at term specificity. So very generic terms like a and the and that occur with every context just tend to clump together. And then you have a lot of terms that you almost never see, and it's really hard to train an embedding for them. Supercalifragilisticexpialidocious. And I've also wondered, instead of initializing embeddings to random numbers, maybe we should initialize them to all 0, and we can see the ones that haven't really changed much, and maybe they're this very specific terms, or maybe they're junk. Yeah, you have to do a lot of data modeling before you get to your embeddings. And I definitely encourage you guys, one thing I'm not talking about is how to actually take these vectors and do similarities in a search engine, which is a place that Lucene has needed to improve for a bit to get all this stuff to work. And Simon has a great talk on that tomorrow, Simon Hughes. So is everyone remember that? It's going to be on the quiz later. Okay, good. So all those ways are still dancing around this idea of aboutness. And it's sometimes interesting to think, like, is there a more direct way that we could understand aboutness? And one way, this is Esperanto, by the way, I already said it right there. One way that some people have thought about this, and this is called out in Tommaso's book too, is in the context of language models. When you're thinking about a language model, think about, one thing I like to think about as a motivator, as one of the directions that language models goes, is translation. So someone said this, and I'm not going to pronounce it because I don't speak Esperanto, in Esperanto, came into this person's head. Something in this head knew what it was about and knew the language to spit it out in a different language. And what is this intermediate stuff? Because we have the problem of our searchers and our documents speak different languages. Is there an intermediate translation that we could train and build that could help us get closer to the aboutness in our documents? And we're going to talk about language models to start out. So first we have to kind of go back to really basic language models. So we can kind of look, if we have a corpus, we can look at all of the utterances of eat, see what the next term is, and we can come up with a table for eat that says pizza is pretty high probability, eat nap, pretty low probability, eat cat, pretty low probability, we hope, eat chair, again, we hope that's a low probability. So we say, okay, pizza is a reasonable guess. And hey, if you want to impress your friends at parties, say, I know about language models, because that's a language model. And you can represent this as a matrix. Now, this is where the math I'm going to show you isn't much more sophisticated than high school math. Because all you need is, here's if you just look at eat pizza, there's our probability, pretty high. Chair and nap are low. Cat, cat pizza, that's low, thankfully. Cat chair, actually, I could imagine a cat chair. Should probably be a little higher. Cat nap, great. That's an idiomatic phrase in English. So here's where we get the math. So we got this right now. And this matrix here this is the same exact matrix, called a transition matrix, because we can sort of see, we can do a transition from one state to another. What is the probability of going from the eat state to the pizza state? 0.02. Now, let's pretend that instead of knowing the exact current word, we sort of have a probabilistic sense of what the current word is. So we have a sense that the probability that the current word is eat is 0.25. And the probability that the current word is cat is 0.40. For some reason, that's green, but it should be blue. And what we can do is we could say, okay, if we just have a rough sense of what the next word is, and I'm sorry, but the cool stuff is down here, people in the back, we can just do matrix multiplication to figure out, okay, if it's 25% chance the current word is eat, then probably the next word is pizza is that 25% times that 0.02% that it's likely to come after, plus, okay, well, there's a 40% chance it's cat, and there's cat pizza, that's really low, 0.001. And all this is just probability. And we get down here and we can say, okay, with some notion of with some probability distribution of the current word, we can get a probability distribution of the next word. So far, so good. Now, and this is just matrix math. So that's matrix math. Now let's say instead of having all V words in our vocabulary, that we have an embedding of H dimensions. So this is a 300-dimensional embedding, and we know that the eat embedding is this. And we know that in our corpus, we know the embedding of the next word in this training example. So this is maybe the pizza embedding, or it's something that clusters close to pizza. We can work backwards and actually move this matrix around using backpropagation to build a transition matrix so that if I put an embedding on the left side and I multiply it into this matrix, it's going to spit out an embedding that's close to the next word. So, after we've trained it, probably whatever gets spit out after eat might be close to pizza or other foods. It's going to be clustered near food, probably. So this is a pretty interesting language model. Now we're actually sort of increasingly working in this probabilistic space. So unfortunately, or fortunately for us humans who have big brains, or we like to think that way, accuracy requires context. So the race is on eat pizza, eat dust. So really, language models work best And if we're going to get at the aboutness we care about in search, context plus word goes to next word. So if we're here and we're like, if we're reading up to here and we're like, what search term kind of goes with this? Dust actually is closer than pizza. If we just use straight embeddings, we're going to say, oh, eat, you want pizza after this. Or straight language model, you want pizza after that. And we don't want pizza, a search for pizza to match this term, this document, right? So remember the stuff we did before. We had our eat embedding. That's just this vector down here. Sorry, people in the back. This is a very vertical slide. We multiply it in this transition matrix, and we get the embedding for the next word. Now, what if we repeat this for every sequence? So what if we take this embedding and try to predict the next word, and the next embedding and try to predict the next word, and the next embedding and try to predict the next word? We can start working with sequences. So how does this work? We have the previous context, and there's a transition matrix from the previous context word. We have pizza. For some reason, I chose to do pizza again. That's confusing. And we could say, OK, what is the probability? Let's multiply this into its own transition matrix and get the next word likely to have come out of this. Let's get the prediction from the previous word and get a prediction here. And these are two different embeddings. This is sort of just looking at the last word. This is looking at the current word. And let's try to weigh these against each other. We can sum them up and get a new context. And there's actually weighting involved here. Well, when you do this and you think about this, and I do encourage you to go home and think about this. I've left a lot of breadcrumbs in this talk for blog articles and things that I found inspirational. Then the combination of looking at these, we can figure out what the next word is, and we can keep going and going and going. And at each step, we can get output too. So we could decide, we could try to pull this closer to pizza. And what ends up happening, when we're training, we put race is on eat, and this is our what we're training against. And what we're carrying forward up here, the thing that's being weighted when you go step to step, is sort of a context that's kind of being remembered through the model. It's an embedding that's sort of close to the context, whereas this is an embedding of just this word, if we did word to vec on just this word. And what you end up happening is you have a transition matrix here that's often referred to as the weights of xh, and a transition matrix at each step, and this is the weight at each step, or the hidden state. And this is just a recurrent neural network. So if you build on top of just a simple transition matrix, you can get to a recurrent neural network. And of course, there's a lot of flavors of recurrent neural networks. Now, this isn't so much so we can all go home and build recurrent neural networks. I would encourage you to look at like TensorFlow or Keras or any of those. But it's important for us for those of us who are relevance engineers to really have an intuition for how this stuff works. And one application for this, of course, of a language model, I don't know how many people are like familiar with the idea that the analysis chain is a graph. And I think that really boils down to the fact that language models are often kind of also a graph. Because if we have a dog is loose, please, and then we can use a language model to predict the probability of the next term using all of this context up to here. Please phone, walk, to, and each of these becomes a branch. Please yodel, please call the animal control dog catcher. And what's interesting is when you do something, I'm showing you term-based language models. Use character-based language models to treat each character and do embeddings for each character. You can basically build a graph that might be every possible spelling correction and try to look at the probability of that string in the language model. And that can be really a powerful technique So, and you can also just, in a term-based system, you could just use this if it makes sense. If this phrase seems very probable, you can use this to generate additional query terms. Now, of course, this is still not a silver bullet if we're only training our language model on our query, on our corpus. If animal control and dog catcher happen in our corpus or something, or if in legalese we have animal control in the index and our users query dog catcher, that's not going to be caught. So to close this off, I want to just start to preview, I think, where a lot of interesting search stuff is going. So the encoder and decoder framework, and I started way back when, maybe 15 minutes ago, talking about translation. And this is what this is. So in addition to showing things examples of existing language, if we have a neural network connected this way with an example in a trained in an example of Spanish, then when it's actually run, this input won't be applied, and we should get words or potentially embeddings, depending on where you pull this out, that get close to the words that are translated for. And when you see that red arrow there, that's a really interesting arrow. And I think one thing you could do with this sort of stuff is you could start to think about how can I translate documents to queries. Instead of translating queries to documents, I like to think about translating maybe queries into the space of the translate documents into the space of the query of the user. So animal control law is an interesting document. Dog catcher, is this relevant? If we have these relevance judgments, we could treat this as a translation data set to translate this language into that language. It's interesting to think what might happen. And of course, this is a 1-0 sense of relevance. The output of the predicted queries here, if we're putting in language, we're putting in our document, we're predicting queries that can be sort of would match that. This output is probabilistic, and we can play with the training data. We can say, oh, actually, dog catcher is really likely, or dog catcher is really likely for this document, but it's moderately likely for this one. So we can play with the probabilities of the queries that are going to be predicted by a document. And finally, I think this the next step beyond this is what I like to think is a pretty interesting field, which is skip thought vectors, where we can do this translation process both before and after. So if we have this encoder RNN, which is the part that's reading in our English or whatever, we can sort of try to decode the sentence before and the sentence after. And this red area here that I had highlighted before actually itself becomes a really useful vector for doing similarity in the notion of translation. So what if I stopped reading right at a sentence, what is this text about? That's really encoded in this vector right here. And you can actually use that for similarity purposes to look and compare different pieces of text. And if you look at a sentence level, there's a lot of interesting things people are doing with this with question answering. And you could do this, you don't necessarily just have to do this but with one query. You could do this by taking my text, encoding it, decoding it multiple times, and then sort of pulling out a vector that's very controlled by all of the queries it's generated for. So, is everyone's head hurting? My head hurts a little bit every time I give this. So to close things off, when we think about aboutness, I think deep learning is really good at these kinds of representations, but I think it still requires a fair amount of work and thoughtfulness to get embeddings, vectors, and representations that match to what you need. But it can apply to a broad range of things well beyond text, which is a huge benefit. I said this before, we have the similarity API, and it's very heavily built towards TF-IDF, and I think for Lucene-based search to compete in the next couple of years, it's got to be more vector focused. And there are a couple things, and I left off parentheses, that give me hope. The limited term frequency filter, I think, is an interesting thing where you can hack term frequencies to be a vector weight. Payloads and payload score is another thing. Eric Hatcher deserves a lot of thanks for doing a lot of this stuff. And also, like I said before, check out Simon's talk. So finally, it's not magic, it's math. And I hope you join me. We have a search, my company, OpenSource Connections, we have a search relevancy community Slack channel, o19s.com/Slack, if you want to join and talk to me or talk to any of us about interesting search issues. So that's it. Thank you guys very much.